All right, we just finished with the rotational partition function, and now we're going to work on the vibrational partition function. In case you're coming in not having watched the earlier videos just before this, let me remind everyone that we're working on the overall ideal gas partition function, Q to the n over n factorial. Q is the molecular partition function, and it has its own factors, Q trans, Q rot, Q vibe, and Q electronic. We've done both of the first two now, and just to remind everybody, Q trans is V over de Broglie wavelength, thermal de Broglie wavelength cubed. Q rot is T over theta rotational. And now we're going to work on the vibrational partition function. So for the vibrational partition function, the model is the harmonic oscillator, and that's good as long as that's good as long as the vibrations aren't too big. If the vibrations start to get real big, if you're at high enough temperature, you can start stretching the bonds a little too much, and then the harmonic approximation isn't so great anymore, but this works just fine for stat mech. And in the harmonic oscillator approximation, our Hamiltonian, our vibrational Hamiltonian, has a kinetic energy part and a spatial potential part. And that spatial potential represents the energy of stretching. In the case of a diatomic, which is what we'll talk about first, it represents the energy of stretching the bond, remember. All right, I won't go through the quantum mechanics because in this case it isn't so simple. But if you do, then the energy, remember we don't need the wave functions, so all we need are the energy eigenvalues. And they are an energy for each value of n. N is the quantum number, and n goes from 0 to infinity, of a quantity h times nu. Nu is Greek nu, the Greek n. It stands for frequency. And it's related to the molecular properties in the following way. The fundamental frequency, nu, is equal to the force constant for the bond divided by the reduced mass for the molecule, for the diatomic molecule. So we talked about the reduced mass last time. If I have a diatomic molecule with atoms A and B, and mass Ma and mass Mb, then the reduced mass is Ma times Mb divided by the total mass, Ma plus Mb. And remember that that can be written as Ma over Ma plus Mb times Mb, where I'm assuming, as before, that Mb here is the light molecule and Ma is the heavy one. And if you think about it that way, then this quantity that's in the parentheses is the fraction of the total mass that's in the heavy molecule. And therefore, it's less than 1. A fraction always has to be less than 1. And that means that the reduced mass is always less than the mass of the lighter molecule. The quantity kappa here, that's another Greek letter, kappa, Greek K, is the force constant for the bond and represents the stiffness of the bond, basically the strength of the bond. If you have a strong bond, let's see what I say down here. Well, I don't say anything down here. Let's go over here then. Let's get some extra space. Then if I have a strong bond, let's say a strong single bond, then kappa will be large. And if I have a weak single bond, then kappa will be small. And so you can see from, and if you have a double bond, then kappa will be large. And if you have a triple bond, like for N2, then kappa will be even larger. And so by just looking at the strength of the bond, you can get a feeling, I mean, not a quantitative one, but a qualitative feeling for how big that force constant is. And then you can see that the frequency is just 1 over 2 pi, the square root of the force constant divided by the mass. So frequencies will be high when the bond is strong. That represents the effects of the force constant, and the atoms are light. Or at least one atom is light, right? At least one light atom. Especially hydrogens. Hydrogens are, of course, the lightest atom. And so the presence of hydrogens always means a fairly small reduced mass, and tends, therefore, to make for high frequencies. All right. Why are the frequencies important? Well, because they control the sizes of the gaps between the levels. So if we look at the energy levels here over on the right, then this set of energies gives a uniformly spaced ladder. All of the gaps between all of the states, the nearest neighbor states anyway, are the same size, and the gap size is always just h times nu, Planck's constant times the frequency. So the bigger the frequency, the bigger the gap size. And the bigger the gap size, as we'll see, the bigger the vibrational temperature. So there was a rotational temperature before, now there's going to be a vibrational temperature, and we'll see that has lots of consequences for what the vibrational partition function looks like. All right, so that's the states and the energies. Let's plug that into our normal way of calculating a partition function, which means we have to sum over all the energies, sum over all the states, really, of e to the minus beta energy for each state. And in this case, where energy is just h nu times n plus a half, that's the sum we have to do. And it's, again, an infinite sum as before, and it's an infinite discrete sum. And in the last two cases, we couldn't do the discrete sum. We had to make an approximation, a high temperature approximation, and turn that discrete sum into an integral, a continuous integral. But in this case, we can do the sum. This is one we can do. And so let's see how we do that. First of all, I'm going to take our Boltzmann factor here, which has this extra 0-point energy factor, energy term. And I'm going to factor it into two pieces, one that contains the n here, and one that contains the 0-point energy 1/2, and that's this term here. So this is the term we're mostly going to be considering. And this extra factor is now, before we had a ZPE term, now we have a ZPE factor that multiplies every one of our Boltzmann factors here. And if we do that, this guy doesn't, the ZPE factor doesn't depend on the index of the sum, n. And so it factors out of the sum. And that means we're left with this ZPE factor times this infinite sum. But that infinite sum is collapsible. It's writable in finite form, and we do it in the following way. We note that this leftover, this Boltzmann factor, can be written in the following way. It's something on the inside to the nth power, and we can call that something x for the moment. Then we have our infinite sum looks like this. And now we note, I mean, there are various different ways of collapsing this sum, but here's probably the neatest way. It doesn't require any trickiness from calculus. We just note that if I let S be my infinite sum, And then I take out the first term, right? The first term is when n equals to 0. That's going to be x to the 0 power. That's a 1. And then I take what's left over and I factor out 1x. So that x has been factored out of everything. Then I get the same sum back. So my sum is equal to 1 plus x times the same sum. And that means I can solve for s. And when I do that, I get that s is equal to 1 minus 1 over x. Remember that x in this case is e to the minus beta h nu. And so plugging that in, and remembering that we have this ZPE factor out in front. Where is it? There it is. So this is our sum now. There's our ZPE factor. So multiplying the ZPE factor and using that, we get our vibrational partition function, which is this ZPE factor over 1 minus e to the minus beta h nu. Pretty simple. In fact, still a little bit more complicated than the rotational partition function or the translational partition function, but still really pretty simple. It will be useful, it will simplify matters, if once again we define a vibrational temperature. This quantity beta h nu is equal to h nu over kT. If we let all this stuff be the vibrational temperature, then that just becomes vibrational temperature over T. And so that's what we do. And rewriting our partition function then in terms of the vibrational temperature, and the vibrational temperature is a property of the molecules, right? So theta V equals a molecular property. It depends on the fundamental vibration frequency. So the higher the fundamental vibration frequency is, the higher the molecular temperature will be. So it represents the vibrational properties of the molecule. Then our partition function becomes this ZPE factor divided by 1 minus e to the minus theta V over T. A pretty simple formula, at least if we're worrying about how it depends on temperature, which is really the only thing it depends on, right? It's that T is the only thermodynamic variable that the vibrational partition function depends on. All right, now, that's the full vibrational partition function, but it turns out that this zero-point energy factor complicates the interpretation of our vibrational partition function. Normally we think of partition functions as counting the available microstates, and that's how we've interpreted both the rotational and the translational partition functions before this. But that's only true if the ground state energy for the system is assigned a value, an energy value of 0. The zero-point energy is not 0 in this case. For n equals 0, the ground state energy is 1/2 h nu. That's the zero-point energy. And the fact that the ground state is not 0 energy gives rise to this ZPE factor, so it will be useful to define a related quantity which isn't quite the vibrational partition function, but is the thing that actually counts microstates for us. It's the thing that's more physically useful to us, as just the old vibrational partition function, but without the ZPE factor. So we just take away the ZPE factor, and that's our Q bar vibrational, and that's more useful to us. We'll use that down below. One other thing while we're here is just before we leave this section where we're talking about the partition function, is to note that this full partition function, vibrational partition function, can be rewritten with a little bit of algebra into this form. Occasionally you'll see that out in the literature. It's also occasionally easier to use than the original one we talked about up here. And I'm not sure what to say apart from that, because it really doesn't tell you anything different than what the original form does. It's just an easier mathematical form. It's a 2 over a hyperbolic sine of theta v over 2t. All right. Let's look at this partition function now, and let's look in particular at the high temperature limits and the low temperature limits. That's kind of going to be our routine from now on. Actually, it's been our routine even in the past, so by now everybody probably is noticing. Let's look at the high temperature and low temperature limits. The first thing to say is that because we didn't make any high temperature approximations in this case, we were able to do the full discrete sum exactly. Our expression for Q vibrational is actually semi-exact. It's as good at least as the harmonic oscillator model itself is, which means it's good all the way down to t equals 0. We don't have to worry about going to too low of a temperature. Even at temperatures much, much less than the vibrational temperature, our expression for Q vibrational is still good. And let me just write it out again. It's e to the minus beta h nu over 2 over 1 minus e to the minus beta h nu. All right, so let's calculate probabilities. This will tell us the populations of the various levels for our harmonic oscillator. That's e to the minus beta e sub n over q vib. Doing the algebra, that gives us one of these two mathematical results. The first one written in terms of beta h nu, the second one written in terms of the theta vibrational. And now we can use those forms to calculate the probabilities at low temperature and also at high temperature. As t goes to 0, beta goes to infinity. So if we plug into there, we can get a result. Also, we can plug straight into there and get a result with temperature. And you can see that as t goes to 0, this whole quantity is going to go to infinity. It's going to go to e to the minus infinity, which means that this whole thing will go to 0 unless we're in the ground state where n is equal to 0. If n is equal to 0, we get e to the 0 here. That just becomes e to the 0, and then you get a 1. And then, so the probability of the ground state at low temperature, the probability of the ground state is 1, and the probability of every other state is 0. Everything is frozen into the ground state. All the upper states have probability 0. That's what you'd expect. Also note that if we look up here a little bit, let me get rid of some of this stuff, that as t, here's Q, as t goes to 0, Q, this is Q bar actually, goes to 1. Actually, this is 1 over Q bar, but anyway, goes to 1. All right, so the vibrational partition function goes to 1 as t goes to infinity. That means one state is available, and only one state is available at low temperature. The probability of the ground state goes to 1. Probability of everything else goes to 0. As you go to high temperature, we have to do a little bit of algebra to get a mathematically useful form for the vibrational partition function. The factor on top, the 0-point energy factor, is e to the minus beta h nu. Beta is, if t is going to infinity, then beta is going to 0, so this is getting very small. If we expand that exponential to just the first power, then we get 1 minus beta h nu over 2. Sorry, there's a 2 there. And in the denominator, we get 1 minus 1 minus e to the minus, well, 1 minus beta h nu. The 1's cancel, and you get, and this guy up here doesn't matter, and so you get 1 over beta h nu for the high temperature limit, which turns into just kt over k over h nu, which is T over the theta vibrational. In other words, just like, remember, for Q rotational, in the high temperature limit, we got T over theta rotational. Now, in the high temperature limit, for the vibrations, we're getting T over theta vibrational. So they're in the high temperature limit, these two guys are the same, except they have different characteristic temperatures. Rotational temperature for rotations, vibrational temperature for vibrations. All right, that's only good in the high temperature limit, and we can still get Q vibe if we like, even when we're well below the vibrational temperature. All right, when the temperature is much smaller than, when the temperature is much larger than the vibrational temperature, and we'll see that the vibrational temperatures are high in this case, so this means you're at a really high temperature, in fact. Then if you look at the formulas a little bit, you can see that the probability is now fairly uniform, fairly evenly dispersed, until you start reaching a fairly high quantum number. In other words, all the probabilities or populations for the lower energy states are all very close to each other. And so you have nearly equal population for all the states up to a value of n that's equal to or about equal to T over theta V. So that's what you'd expect, right? If your temperature is high enough so that you've got a lot of thermal energy compared to the gap spacing between the levels, then a lot of levels are going to be populated. We will see later that this high temperature form also corresponds to the classical expression for Q vibrational. In other words, if you treat the problem as a classical harmonic oscillator rather than a quantum harmonic oscillator and do the stat mech that way, and we'll look a little bit at that, then you'll get this result. So the high temperature limit is the classical limit, and that tends to be true, that is true, in fact, in every case. So if you're in the high temperature limit, you can treat the system classically, as if it obeyed classical mechanics, and you'll get the right answer. In general, we'll see one example of that later. All right, let's look at these vibrational temperatures now for real molecules. So remember that the vibrational temperature is h nu divided by k, so it's proportional to the fundamental vibration frequency for each molecule. And remember that the fundamental vibration frequencies are the square root of the force constant divided by the reduced mass. So molecules with reasonably strong bonds, and therefore largish force constants, or very small reduced masses, tend to have large frequencies and therefore large vibrational temperatures. The biggest one on this chart is for H2. It's got a reasonably strong bond and it has a really small reduced mass, so it's got a fundamental vibration frequency of 4,400 centimeters to the minus 1. That gets converted directly to the vibrational temperature, which in this case is 6,000 degrees Kelvin. That means that for H2, we don't reach the vibrational temperature where things start to get populated, where the ground state isn't the only populated state, until we're at the temperature of the surface of the sun. If we look across then at the the vibrational partition function, let's do a calculation for that and see why we're getting just one. That means only one state is really occupied, right? And so let's look and see why that's the case. So the vibrational partition function, the vibrational partition function without the ZPE factor, so counting microstates, is 1 minus e to the minus theta v over t. And now we're seeing that theta v is around 6,000 degrees. Let's just say 6,000 degrees. But if we're at room temperature, T is only about 300 degrees. And so theta V over T is about 20. And that means our Q vibe here is 1 over 1 minus e to the minus 20. That's essentially 0. And so we just get 1. That's always going to be true as long as our temperature is well below the vibrational temperature. We're always going to get a small partition function, basically 1. We're only going to have one state occupied as long as we're well below the vibrational temperature. And now look at these vibrational temperatures. Here's a whole bunch of molecules, diatomic molecules. And the lowest vibrational temperature on the chart here is already still 1,000 degrees, 4 times bigger than room temperature. And so we're just not getting any population for anything other than the ground state for any of these vibrational partition functions. If you ignored the vibrational partition function altogether for most molecules, it wouldn't make very much difference in the answer. So for oxygen, it's got a double bond, a strong bond, still 2,200 degrees for the vibrational temperature. Nitrogen's got a triple bond, so pretty high vibrational frequency, not as high as H2, notice, because H2 has that very small reduced mass. But still, a high vibrational frequency and therefore a high vibrational temperature. And then HCl and HF don't have especially strong bonds, but they have a light atom, and that also makes, again, the reduced mass small. And so the highest vibrational temperature on the chart, apart from H2, is for HF here, which has a pretty strong bond and the one light hydrogen atom. All the populations are 1. Finally, down here for CO2, we have a polyatomic molecule. It's linear, and it has 3 atoms, and for that reason, it's got more than one oscillator. It's got 4 normal modes and therefore 4 oscillators. And so that's why there are 4 fundamental frequencies here and also 4 vibrational temperatures. In order to understand that better, we have to talk about polyatomic molecules and normal modes, and that's what we'll do next. All right, so let's do one more thing before we look at the normal modes, and that's to see what happens to Q vibe when T is actually equal to the vibrational temperature. In that case, just plugging the numbers in, Q vibe is equal to about 1.6, which means that even when you're at 6,000 degrees for hydrogen or 2,000 degrees for nitrogen, you're still not getting a very many occupied states, and Q vibe is still only about 1.5 or maybe 2. All right, polyatomic molecules now. If I have a polyatomic molecule, let's take water, for example, or CO2 for that matter. 3 atoms in both cases. Then it takes 3 degrees of freedom, 3 position coordinates, to specify the location of every atom in the molecule, so a total of 9 coordinates altogether, or 3 times n coordinates altogether, for n atoms in the molecule. And n is equal to 3 here, and n is also equal to 3 for CO2 in this case. We're going to use 3 of those coordinates to specify the location of the center of mass. So that's 3n minus 3 remaining coordinates. Then we're going to allow the molecule to rotate, and for a nonlinear molecule like water here, there are 3 rotation angles. Let me show a picture down here, right? Here's water. And there's in order to give the orientation of the water molecule, I need a theta angle, I need a phi angle to orient it in 2 degrees of freedom. But then I can also spin the molecule around that axis. And so there are 3 orientation angles for a nonlinear molecule. But if I have a linear molecule like CO2, then I don't need this third angle, and so there are only two orientation angles. And so in the case of water here, I started with 3 in coordinates, I subtracted the center of mass, now I'm subtracting the orientation angle coordinates, and so there are 3 in minus 6 coordinates left over. Those are all going to be vibrational coordinates. In the case of CO2, which is linear, I started with 3 in, I subtract 3 for the center of mass, I subtract just 2 now for the orientation angles, and that's 3 in minus 5 vibrational coordinates that are left over. And that means that for water, for a nonlinear molecule, there will be 3 in minus 6 normal coordinates. And for a linear molecule like CO2, there will be 3 in minus 5 normal coordinates. So for water, which has n equals 3 atoms, there will be 3 normal coordinates. And for CO2, which also has 3 atoms but is linear, there will be 3 in minus 5, 9 minus 5, which is 4 normal coordinates. So what does that mean? Well, each normal coordinate has its own independent harmonic oscillator. Which means that each normal mode has its own independent ladder of states, each its own independent fundamental frequency, and therefore gap size. Each will therefore have its own separate vibrational temperature, and therefore its own separate vibrational partition function. And the overall partition function for all vibrations, all normal modes combined, is just the product. They're all independent, right? So it's the product of all the independent normal mode vibrational partition functions. So up here, for CO2, returning to where we were, 3 in minus 5 is 4 normal modes. Here they all are listed down here. There's an asymmetric stretch where the oxygen atom and the carbon atom sort of pinch together, and on the other side, the carbon atom and oxygen atom stretch each other apart. There's a symmetric stretch where the oxygens move in the opposite directions and the carbon basically sits still. And then there are 2 bending modes where the carbon atoms move up, say, the oxygen atoms move up, but the carbon atom moves down. Or else they do the same thing, but now out of the plane of the page here. So those 2 modes are identical, therefore they have identical frequencies, but there are still 4 of them. And the overall partition function then for CO2 will be Q, let's call this 1, this 2, this 3, and this 4 will be Q1 times Q2 times Q3 times Q4, but Q3 and Q4 are the same, so it's Q1, Q2, Q3 squared will be the overall partition function for CO2. All right, that's it for vibrations. Next time we'll talk about the electronic partition function.